Hello and welcome to 1039 here. Just give me a second to set up the action. I will talk in Heidegger 1039 more about the quantum epoché because it was absolutely fascinating, and I think it could be one of the biggest insights for some while here. And it was also very helpful in realizing how we have understood in this journey these now 1039 lectures long. It's a grand trip spanning over years and so much material, and I realize the doing was the understanding long before there was an aware understanding, or maybe that's the reflective consciousness awareness, and that we don't really appreciate the doing understanding, and we don't sense it, and therefore we assume it not to be there. We assume our all small interactions with the world, our boundedness to the reality, we devalue that, and we don't think a change can be made, and therefore we start dreaming about other words. But the change is possible. Pylkkänen, in his article The Quantum Epoché, is pointing to that by doing things, most of the job is done. I would say everything is done by then. And then you can just let the things come to you. And of course that is part of the Piotto or mescaline experience, but it's so much more, because it encompasses your intellect, it encompasses your theories. There is liberty within the theories. They do not have to be attacked head-on, like one combat tank striding towards another one, trying not to show any lenience whatsoever. I think lenience could actually work. And it also gives me association to how when we lack the energy and direction, we make up these other things, the divisions and the prioritizing and the marginalization. And those things, they don't work really well. They don't have an effect. They are dependent on what it is not. They are weak, not very convincing. And this is where the argument Derrida made when defending his friend Paul de Man, that he undermined the Nazi intention by using too many divisions, by placing the reader in a bystander place. Well, at least encourage him to be in a bystander place, because in the end it's the reader himself who chooses. This truer, more genuine way of being doesn't need comparison, doesn't need division. It speaks for itself. It is its own truth. It's not truth dependent on others or other or something. But let's cut to the chase and let's continue. I feel that Bachmann seems to be very interesting as well. I would take a gander into his. There are a number of reasons, Pylkkänen continues in his article. There are a number of reasons why bringing together phenomenology and quantum relativistic physics is potentially fruitful. For one thing, this might enable new, more insightful phenomenological descriptions, as Bohm's above-mentioned discussion on time consciousness illustrates. Also, the methodological insights of phenomenology might prove useful when trying to make sense of the interpretational puzzle of quantum theory in particular. For example, we will below consider how a kind of epoché, or a suspension of assumption about reality at the quantum level, seems to be required to make a coherent sense of the results of some quantum mechanical experiments. Further, such bringing together of phenomenology and the new physics also seems to be in line with the very criteria phenomenologists typically set to themselves. The empirical phenomena encountered in quantum and relativity physics have given rise to a new philosophical situation that poses a challenge not only to philosophy in a Heideggerian sense, but also to phenomenology broadly understood, given the emphasis that later phenomenology puts upon historicity and situationality. It is somewhat ironical that there have been so few phenomenological discussions of the new epistemic and ontological situation opened up by quantum theory and relativity. However, this also implies the possibility for much fruitful research in the future. For example, there has been an extensive philosophical discussion on the meaning of quantum theory since the 1920s. Connecting this rich discussion with relativistic, maybe I should make a change that, sorry. Connecting this rich discussion with relevant aspects of phenomenological thought suggests a vast research program with possibilities of mutual criticism and enrichment between the two approaches. For example, of such attempts see Honor 1982, and especially in relation to post-phenomenology. Look at it in Plotnitsky, my old favorite, 94, and Globus of 2003, and Pylkkänen in 1998. And of course, as already mentioned, this special issue, as well as the previous research of some of its contributors, marks significant progress to a new synthesis of phenomenology, physics and biology. In this article, the theme of phenomenology and quantum physics is tackled by examining some basic interpretational issues in quantum physics. One key issue in quantum theory from the very beginning has been whether it's possible to provide a quantum ontology of particles in motion in the same way as in classical physics, or whether we are restricted to stay within a more limited view of quantum systems. in terms of complementarity but mutually exclusive phenomena. In phenomenological terms, we could describe the situation by saying that according to the usual interpretation of quantum theory, especially that due to Niels Bohr, quantum phenomena require a kind of epoché. That is an assumption, or a suspension rather, of assumption about reality at the quantum level. However, there are other interpretations, especially that due to the David Bohm, that seem to re-establish the possibility of mind-independent ontology at the quantum level. But as we will see, even such ontological interpretations contain novel, non-classical features, which require them to give a special role to phenomena or appearance, a role not encountered in classical physics. We will conclude that while ontological interpretations of quantum theory are indeed possible, quantum theory implies the need of a certain kind of epoché, even for this type of interpretations. While different from the epoché connected to phenomenological description, the quantum epoché nevertheless points to a potentially interesting parallel between phenomenology and quantum philosophy. Our discussion also connects to some of the central issues discussed by Kaufmann and Gare in the prologue to this special issue of the article. For one thing, there is a question of measurement in quantum mechanics. Kaufmann and Gare explore the possible role of mind in quantum measurement. They present the triad, a new view of quantum mechanics, which has, cite here, actuals that are ontologically real and defined as obeying Aristotle's law of the excluded middle, possibles which are ontologically real and are defined as not obeying the law of the excluded middle, and mind, consciousness with qualia and free will, doings at measurement. In short, res potentia, res extensa, linked by mind at measurement. Now Bohm showed in 1952 that measurement-like processes at the quantum level can take place objectively without any active role of human consciousness. For good introduction to how Bohm theory solves the measurement problem, you can have a look at May 2013. I'll try to put in links here. In Bohm's quantum ontology, an electron is assumed to be a particle guided by a new type of quantum field. Just excuse me for a second here. Let's continue here. Sorry about that. Bohm showed in 1952 that measurement-like processes at the quantum level can take place objectively without any active role of human consciousness. In Bohm's quantum ontology, an electron is assumed to be a particle guided by a new type of quantum field, which latter is mathematically described by the Schrödinger wave function. In Kaufmann and Gare's terms, Bohm showed that rest potential, understood as quantum potential which arises from the quantum field, acts on res extensa, the localized particle aspect of an electron, in such a way that we get definite results of measurements. and that without Schrödinger cats or many worlds. All these can happen objectively without the need for human observers or minds. According to the Bohm theory measurement, processes are a special case of quantum processes, such as transitions between stationary states, which later takes place in nature completely independently of human intervention. Well, thank you very much for that, Bohm. That solved a big problem for me. Why is human intervention not necessary from some aspects? Well, the mind takes part in quantum physics. It has a decisive role, and therefore it means that if the mind is classical, that would be automaticated, and in the end won't be needed to have an active mind or have a mind round, because the mind itself is classical. It's just when the mind no longer is classical, a change, a collapse of the way function can happen. Obviously, we have been ignoring the subject part, and we thought about the mind as being the same all the time. It is not the same at all. It's a completely different mind. And that mind cannot have any part in the collapse of the quantum wave. I think this is what Bohm is pointing to here. Yeah, listen to this. However, a deeper study of Bohm's theory suggests an affinity with Kaufman and Gare's approach. Note especially that Bohm and Haley suggested that the quantum field is not pushing and pulling the particle mechanically, but is rather informing the energy of the particle. Bohm characterized the quantum field as containing active information and saw this as a primitive mind-like property of elementary particles such as electrons. This in some way similar to Kaufman's and Gare's idea about some kind of proto-consciousness being present in quantum processes. I mean, that's a really decisive point there. If you do division, if you preempt experience, you will both have a mind that is mechanical, terminable, not consistent over time, and you will have a world at the same time that show up those features as well. The mind and world go hand in hand. And trying to only change the world, or the conception of the world as the New Agers and the hippies did, bound to catastrophe, because they never changed their minds. They never took up the subject pole. Instead they took, I think my explanation with Gary Zucker and Fisher Capra and et al., they just use it for their own dreams. And although it had some pretty incredible positive effects, bringing billions of dollars to the research field, it did actually do that. It was no good for the ones who read the books, because they once more established even more the idea that the mind not taking part in the whole thing. And the mind that is informed in such a way will become passive, and passivity means also ontologically passive. It will have those features. It will be of that kind, so to speak. It will be a completely different brain, will not be the same brain. How can I say that? Well, the brain is the fractality of the brain. That is the thing that does the observation or does the thinking. And the classical brain is different thereby. But it is literally different also from a classical physical viewpoint. Remember, that brain doesn't seem the same in an MRI nor in an electroencephalogram, even if you were to diagnose it with an electron microscope. You will find the N2 neurons. And saying that such a brain can experience quantum field changes and such stuff as Gary Zukov and many other quantum physicists had claimed is pure nonsense. And I think this is the point of the article. It's not until you change the world will change. It sounds like a cliche, and of course it is, sorry about that. But what can I do? This is how it is actually. But you have already heard how different it sounds. Active perception, that there are three times more information going out to the neurons. Although that it's showing that system is completely different from the classical world. And you never ever get anything for free. If you believe in the classical world, this is how you will construct the whole system. It's no natural way of looking at things. You are classical through and through. You're even more classical in your brain than your outside world is. That's where you're really classical. And that will not change automatically or change by understanding, but it will yield to change in practice. It will absolutely in the end yield to practice. And then comes the understanding. First you do something, and then understanding comes as a free gift, like a lottery ticket that you forgot and you decided to scratch. Then you enter reality. There is also here a connection to the issue of exophysics, which presupposes a detached observer, and endophysics, which sees the observer and measurement as part of the domain that needs to be accounted for. First of all, there is a sense in which Bohm theory allows us to retain an exophysical perspective to the universe. For if we assume that human observers have no significant influence upon the quantum state of the universe, then we can, for all practical purposes, ignore measurements and the active role of human observers in our general description of nature. Well, here is a parenthesis. Remembering, however, that Kantian considerations suggest that we probably have no perceptual and conceptual access to nature from a non-human perspective. However, there is also a sense in which the Bohm theory fits very well together with endophysics. For one thing, the Bohm theory provides perhaps the clearest available account of how the process of measurement can be accounted in terms of quantum theory itself, thus enabling a coherent endophysical discussion of quantum measurement. Bohm also sketched how the consciousness of the observer could be included into the picture. The basic idea is that quantum ontology needs to be extended. At the quantum level, we have particles guided by the quantum field of information. Bohm speculated that in the context of complex biological systems, such as brains, there is likely to be a whole hierarchy of such fields of information, ranging from manifest to more subtle and actively enfolding and unfolding information about each other, involving guidance relations. Mental processes and conscious experience could then come in a more subtle level of organization. Through the hierarchy of fields of information, mental processes and perhaps a kind of free will could make a difference to a more manifest processes via the quantum field, suggesting another affinity to the ideas of Kaufman and Gare. Further in his more general implicate order scheme, Bohm sketched how both biological and mental processes could be understood in relation to the physical world, as described by quantum and relativity physics. The above considerations are meant to indicate that there are rich connections between Bohm and Haley's natural philosophy to the general approach discussed in this special issue, especially in its excellency brought out by Kaufmann and Gare. In the rest of this article we will, however, focus on the question about the role of phenomena or appearance in Bohr and Bohm's interpretation of quantum theory. Nota bene, there are two different people, Bohr and Bohm. Let's start with Bohr. Niels Bohr, the second chapter of the article, Quantum Epoché. Question here, can we have an ontological description of quantum systems, say of particles such as electrons? In the domain of classical physics, it is possible to measure simultaneously the position and momentum of a particle with arbitrarily good accuracy within a single phenomenon, and thus one is allowed to postulate a particle ontology, in other words, to make the transition from phenomena to ontology. Usually in classical physics, one just talks about the particle and its properties, ignoring the phenomenon in which these were measured. In phenomenological terms, this reminds us of the natural attitude. We take for granted that the objects that appear to us in experience also exist when not being observed. We then slip from appearance to reality without noticing it. However, according to Niels Bohr, we cannot make a separation between the particle and the experimental arrangement in quantum situations, because the quantum action that connects them during the measurement is indivisible, unpredictable, and uncontrollable. For Bohr, this meant that we cannot analyze the quantum phenomenon and assume that we are getting information about a separately existing particle with well-defined properties. In other words, there is no single phenomenon in which both the position and the momentum of a quantum system can be accurately measured at the very same time. Thus, implied Bohr, it is not legitimate or meaningful to postulate an ontology in when a particle has simultaneously a well-defined position and momentum, as these supposedly exist irrespectively of any act of observation. In phenomenological terms, we could say that Bohr was calling for a kind of epoché in the context of quantum phenomena, in the sense that we need to suspend our classical habit of conceiving of a well-defined observation-independent ontology of particles in motion. So the issue for Bohr seems to be when it is legitimate to postulate an ontology, or to put it differently, what does the incompatibility of phenomena associated with a single system imply for the ontology of that system? The following quote captures many essential features of Bohr's subtle ideas. The crucial point implies the impossibility of any sharp separation between the behavior of atomic objects and the interaction with the measuring instruments, which serve to define the conditions under which the phenomena appears. In fact, the individuality of the typical quantum effects finds its proper expression in the circumstance that any attempt of subdividing the phenomena will demand a change in the experimental arrangement, introducing new possibility of interaction between objects and measuring instruments, which in principle cannot be controlled. Consequently, evidence obtained under different experimental conditions cannot be comprehended within a single picture, but must be regarded as complementary in the sense that only the totality of phenomena exhausts the possible information about the objects. End of quote. There was a rather long quote. The phenomenological reader noticed how the measuring instruments play a transcendental role for Bohr, as they define the very conditions under which the phenomena appear. A new kind of wholeness in physics is implied by the fact that no sharp separation between the behavior of atomic objects and the interaction with the measuring instruments can be made. This means that we typically cannot assume, when looking at the result of measurement in an experiment, that the results refers to the behavior of the atomic object as it unfolds independently of its being measured. This is in stark contrast to the situation in classical physics, where the theory allows us to calculate the influence of the measuring instruments to a good approximation, and in this way gets an accurate information about the behavior of objects as we want. Note also how Bohr says that it is because of such indivisibility or individuality that different experimental arrangements are mutually exclusive. If I want to measure the movement of a particle in a situation where I am measuring its position, I need to make changes in the experimental arrangement. However, such changes introduce new possibilities of interaction between objects and measuring instruments, which Bohr says in principle cannot be controlled. This connects with the uncertainty principle and Bohr's assumption that the quantum of action needed in its measurement is uncontrollable. After the changes in the experimental arrangement required to measure the moment of the particle, I can no longer measure its position. Thus, the experimental arrangements are mutually exclusive. Bohr further emphasizes that we cannot comprehend the evidence for such mutually exclusive arrangements within a single picture. And yet, we have different kinds of evidence about the same object. How should we consider such evidence concerning the same object? Evidence that is obtained from mutually exclusive, incompatible experimental phenomena. Bohr says that we must consider such evidence as complementary. Notice that complementary here cannot be understood in the sense of two parts of a single picture. Very important. Such a good part. Pylkkänen, I really like him because he points this out. So many people think that the complementary means that we put two things together to get a whole picture. That is not so. This is not how it is. Not at all. I would say that's the furthest you can get from how it is. And that idea will destroy all understanding of complementarity. It's better to understand in the sense of the experiment. And only by thinking clearly and carefully how an experiment is executed, then you can have an understanding. Well, it makes a difference actually how it's constructed. And that is a fact that many scientists forgets. It is not part of the experiment itself, but it's very important to show that the observer is still there, having an effect. but it's easily forgotten because you can do the experiment anyway. You see the difference? One point is completely scientifical, Bohr makes it, but it also has a trait of something other, of the why question, one could say, complete simplification. But you can still do the experiment, and you can do it advancedly. But as long as you forget this very important little aspect when changing the experiment, everything will be changed. It's so easy to forget. And I would say this is absolutely parallel how we forget that we do things all day long. That the two-handed we do have become dull. And therefore our mind becomes dull. It can sound advanced. It could be the advanced scientists who claim that the observer doesn't have a role to play. It goes hand in hand. Classical physics maybe henceforth should be just having the attribute of being clumsy or a bit dull, not very exact. And we can enter into classical physics, keep it, but make it more exact, more consistent. And this is also doing it in the right order. If you are this clumsy person, you will also have a clumsy perception. And that clumsy perception cannot avoid other than bring the world as a capture, as a conquest. This is what a classical physical brain does. It will always do that. You should expect it to do it. But that's the first hint, that's the first step of the path, to recognize that within yourself. Then you can go further. Then you might understand you can put a lot of effort in doing things, projecting and so forth. There are mental doings you will also experience, because projection is a doing. And then you will access a completely different mindset, a different way the mind could work. That is not present there now. It cannot be present there. And if you say it's present here like Garizuka, it's wrong. But the possibility is there. By being more specific, more exact. And this of course could only be pointed out by Niels Bohr. He was so incredibly sharp, and especially that's a specific scene in Brussels where he was really caught off guard by Albert Einstein. And to say that Albert Einstein missed something is an exaggeration. Everyone in this world misses that. But still Niels Bohr, late at night at the hotel at Brussels Square, the old square, could find the mistake, that there is an interaction, that there is somebody sort of meddling with the thing. The observer was so hard to spot, but he found it, and in the revealing moment when he presented it to Einstein, Einstein gave up. He never ever mentioned anything to Niels Bohr. But think about this. If Niels Bohr didn't have the stamina, the energy, the sharpness, or the correctness, or the exactness, he could have lost. And then you think, well, it would have been discovered later. Never, would never been discovered later. It had to be in that moment. That is very important to understand, because the mind does play a role, and it could have withdrawn there, and Einstein could have won, and we could have this classical mechanical quantum physics. You have to understand that. That moment, close to Solvay, where they were staying, very nice maisonette that offered his whole palace de Solvay. If that did not happen there, could well be that we wouldn't have a quantum physics today. Not in the way that we have today anyway. The sharpness of Niels Bohr. Well, that's interesting enough. I need to continue with this, because this is absolutely hot stuff. I say thank you very much, and have a very pleasant afternoon. Bye bye for now.